Okay, this is more statistics, exercise 7F, uniform continuous distributions, obviously following on from a lot of other work we've seen in chapter 7 on continuous distribution. So let's see if we can start to use some of those ideas and blend them together. Now this actually builds on some work we saw before, which was called the discrete uniform distribution. Now in the discrete uniform distribution, everything that can happen has the same probability. So for instance, you think of a die. When you roll a die, everything has the same probability. It goes from 1 to 6, and therefore all probabilities are equal to a 6. And you'll notice, in general, that's written in terms of if x is uniformly distributed, then probability that x is any number is the same thing. Doesn't matter what the x is, it's still 1 over n. Because there are n things that can happen and they're all equally likely. Now the expected value, we've got a formula for that, and the variance, we've got a formula for that as well. So we've got an example here. An electricity company has a line running 50 miles between two remote towns A and B. Every 5 miles is a substation. So by definition, every 5 miles, you won't be supposed to learn that in total there's 10 substations. Find the probability of there being a problem at either of the first 2 substations. Well, there's 2 of them, so presumably it could be either there or there, or it could be both, I suppose. So anyway, we've got a probability that x equals 1, or probability that x equals 2. It seems obvious that the answer is 2 out of 10, or 0.2, or 5th, or whatever you want to write it. The expected distance of the problem from A, again, expected, so I'm kind of thinking I'm going to use this formula. N is 10, so that's 11 over 2, so I'm expecting my average distance, if you like, for me to have to go and fix it, is 5.5. Is this kilometres? I can't remember, or miles? It's miles. And the variance of the distance from A, again, I'm just going to chuck in the formula. So I'm going to do 10 squared minus 1 over 12, which is 99 over 12, whatever that simplifies to. And so I didn't even bother, there you go. So there's my 3 answers. Now we are looking today, though, at something called the uniform continuous distribution. And as we've already seen, we get a variety of distributions, and they can, usually there's some kind of curve for them, isn't there? And they can go up like that, and it might just stop. So it might be between 0 and 2 it does this, and everywhere else it's 0. And we've seen loads of functions written like that. Now this one is different. This is the uniform distribution, which basically means between 2 values, A and B, so let's say again 0 and 2, everywhere between them is equal to the same amount in terms of its probability. That means either side of it, it's 0. So again, I picked 0 and 2, it can be any numbers, hence down here it says A and B. And this is f of x again. Now just bear in mind, because the probability has got to equal 1 still, the total probability is 1, you can see that allows me to work out this height here. And this height here is got to be equal, in this case I think it's got to be equal to a half. Because a half times by the width of 2, we should now know the area of this thing effectively has to equal that 1, and so the height is a half in order to do it. And in more general terms, you take away the distance, one the other, and it's 1 over b minus a. And as I say in my case, it's 1 over 2. This is in the formula book. It's a relatively straightforward formula, but we just, to be honest, most people miss it. I've seen loads of questions where at first I thought, well, I don't know how to do that, and I thought, oh, it's just a uniform distribution. So this word uniform means quite a lot. It means we can use this formula. Prove that if x is a random variable following a continuous uniform distribution over a comma b, so this is the proof. I'm going to prove to you that this is true. And I suppose the way you've got to do it, you've got to attack this in terms of the standard definition of what E of x is. It's E of x, of course, is we've already seen you do x times f of x, and you integrate between the 2 points, so from a to b, dx. And if this is the case in this case, now I already know what f of x is. I told you that on the last slide. It's 1 over b minus a. It's a bit rubbish, but that's what it is. And therefore, when I substitute that in here, I get x times by 1 over b minus a dx. Now this is just a number, as we saw before, and in the example I had before it was a half. So I can take that out as a common factor, almost a constant number, and that just makes it this. So therefore I integrate x, which makes it a lot easier, and if I integrate x I get x squared over 2. Don't forget I've still got this b minus a at the front. I could write that as 2 lots of b minus a. That's between a and b. So if I put b in, I get b squared over 2 lots of b minus a. And I've put the a in, I get a squared over 2 lots of b minus a. Be aware then that's b squared minus a squared over 2 lots of b minus a. And the thing I notice about the top, that's the difference of 2 squared, so that's b plus a, b minus a over 2 lots of b minus a. And that must cancel out, and that presumably gives me b plus a over 2, which was the formula. Okay, so it seems to work quite nicely. You can do a similar thing for the variance, and I'm not going to do it now. You might have to actually do it in the exercise, I can't remember. But the formula that you need to know then, again, I think you have to learn these. I'm not necessarily thinking these are in the formula book. But E of x is a plus b over 2 and b minus a over 12. In fact, did I say this was in? I had it at the end of this. Oh no, this is in the formula book, but not necessarily these two formulae. So I think you're going to have to learn these two. And this one, it means that you wouldn't invent this yourself necessarily, but it just comes from working out E of x squared. You should remember that E of x squared minus E of x squared is equal to the variance. So if you worked out the E of x squared thing and took away what we've just done, you should get this formula. So anyway, here's an example of that. When a measurement is quoted to the nearest kilogram, it is equally likely to be anywhere within 0.5 kilograms of a stated value. Okay, let's go back to that. I don't know why it's gone back. So we can be within 0.5 of a stated value, and it says the large number can be rounded to 42. And obviously you can go a bit lower than it and a little bit higher than it according to this 0.5 rule. So I think we're basically talking, we've got 42. It's a bit of a wordy, rubbishy question. Let's get away from that and get some numbers out of it. I think we can go down to 41.5 and up to 42.5 like any number can. So we got a bunch of numbers that are all equally likely because this is a uniform distribution. I assume it's a uniform distribution. Yes, it's equally likely to be anywhere in the range. So this basically is what tells us it's uniform, I suppose. So it's a uniform. It can be any number. It's measurement, so it's continuous distribution. Okay. Bearing that in mind, it says find the probability an object quoted as being 42 is actually more than 0.3 away. So right, more than, so 42.3 I suppose, and 41.7, but it wants to be more than that, so it has to be in this range and in this range. And look, just look at it, that's 2/10, that's another 2/10. I reckon this is 0.4. Remember what the formula said? It was just f of x is 1 over b minus a. So in this case I just think I mean, effectively this has got to be 0.2 for this section, and this has got to be 0.2 for this section. So I think 0.4 overall is what we're talking really here. I don't think it's a particularly tough question. But the standard deviation for this then, we've got a formula. We just remember that formula that it said, we wrote it down before on the last slide. So the variance, which obviously we're going to use, is b minus a. And it says squared over 12. Find the standard deviation of the difference between the quoted value and the true value. I'm just trying to get my head around. Find the standard deviation of the difference between the quoted value and the true value. Now, of course, what we're doing then is we're finding the variance that the quoted value was. We're saying they got 42. But the true value, I suppose, is the x. So this is the variance actually we want to find. And we should remember, let's just use a bit of our knowledge of when we play around with the variance and the expectations and stuff, you should remember that this is probably better written variance of minus x plus 42. And if you add 42 to a variable, you should remember that the variance doesn't change. So this is really the same as the variance of minus x. And if we find the variance of minus x, you can think of that as the variance of minus 1 times by x. And you should recall that that really is the variance of the x. And you bring that minus 1 to the front, and squeeze it in here, and you have to square it and times it. And of course minus 1 squared is 1, so this is really the same as 1 times the variance of x, which is really the variance of x. So having done all that, I've come back to the conclusion, although it says find the variance of 42 minus x, it's actually exactly the same as the variance of x, which is where I started with by quoting the formula. So how wide apart are these things? It says b minus a. Now b minus a is well, I suppose this is really, I mean, look, just don't forget, when I talked about this earlier on, this is my b value, and this is my a value. So what I'm really doing, I'm saying 42.5 minus 41.5. So in this particular case, that has a difference of, I suppose, 1. And I square it, and I divide by 12. I reckon the answer is a 12. Whatever that is as a decimal. Let's see what it says the answer is. Oh, square root, of course, yes. Because mine is the variance, and this is the standard deviation, so I'm meant to square root that, 112. Okay, I mean, it's a bit weird, isn't it? It's a bit wordy. So just remember, we're going to, in class, play with this. But it was interesting, in order to get that, I had to suss that. That's what I wanted, but that it was really the same as the variance of x. I suppose they could be similar things. So anyway, I want you to have a look then at this exercise 7F in class. Might need a bit more explanation at the start of the lesson, but your standard continuous uniform continuous distribution. There you go.